Okay, guys, so if you look in Schoology for today, notice I added a new folder which says 4 to 6 weeks because we are beginning a new marking period. So you want to click on that, and then today is January the 25th. It is a Monday. Okay, and so you click on that, and I've already posted the work for both my A day and my B day classes. Okay, so in this case, today is Monday. Now, today we are introducing a topic known as momentum. We're going to talk about a momentum. We're going to talk a little bit about impulse today, and then as soon as we get done, going over these examples, I'm going to open up the momentum and impulse concept assignment. But our main focus today is introducing momentum. And of course, I have some notes here. And so the notes look like this. It basically defines what momentum is. Momentum is defined as the quantity of motion of a moving body. It is measured as a product of its mass and velocity. So guys, this is probably one of the easiest equations you're going to get in this class all year. Whenever you're calculating momentum in physics, momentum is equal to mass times velocity. Okay. Now guys, in physics, whenever we represent momentum, we tend to use this symbol here that looks like a letter P. So anytime you see this letter P in physics that looks something like this, we use that to denote momentum. Momentum is equal to mass times velocity. And we know if the units for mass are in kilograms and the units for velocity are in meters per second, then that means momentum is kilograms times meters per second because you multiply these two units to get momentum. Okay. So that's what momentum is. Momentum is defined as the quantity of motion. In other words, guys, momentum is a numerical measurement of an object's overall motion. So what do I mean by that? Okay. Well, guys, imagine a linebacker. So imagine a linebacker that's running, okay, and he's about to tackle a quarterback. Okay. Guys, if a linebacker is running and is about to tackle a quarterback, while that linebacker is moving, physicists will say that that linebacker, he has momentum. There's a certain quantity to his motion. If the linebacker is running at a small rate, so in other words, let's say he's running at 2 meters per second, then we would say his momentum is low. But let's say he's running at 7 meters per second, then we would say his momentum is high. Okay, so depending on how fast the linebacker is running, he may have high and low momentum. If he's running very fast, he has a lot of momentum. If the linebacker is running very slow, he has a small momentum. So that's what momentum is. It's the quantity of motion. It's a numerical measurement of motion. And again, it's equal to an object's mass times velocity. So guys, you can easily imagine that if you have two running backs and they're both running at the exact same speed, the running back that weighs more obviously has more momentum, right? Because momentum depends on those two things, mass and velocity. And guys, by the time we're done with this Zoom call, I want to explain why is it that why is it that physicists assign a numerical value to motion? Because as it turns out, this way of thinking about momentum is very useful when it comes to analyzing collisions. So this is why it's important that we assign a numerical value to motion, and we call that momentum, which is the product of mass and velocity. Okay, so I want to begin by introducing a few terms because in the assignment that I have today, that I have posted today, you guys are going to have to know these terms in order to match them with their appropriate definitions. Okay. So, let me see. Do I need a blank sheet of paper here? No, I probably don't. Okay. So, guys, we have already said that momentum is defined as the quantity of motion. It is the product of mass and velocity. Okay, so let's go ahead and do this. Do these first few problems together. And guys, please pay attention to this because you're going to see more examples of this in the assignment today that you guys are going to work on by yourselves. Okay. So momentum by definition is the product of mass and velocity. That means this right here needs to match up with letter F. So we're gonna begin by matching definitions here. Okay. Now, um, here's another term we're going to see this week, and this term right here is called impulse. Okay. Impulse basically is defined as how an object changes momentum. So if you have an object, let's say an object is in motion, and it slows down, obviously its momentum changed. Okay, so that change in momentum is what we refer to as impulse. So that means letter 2 is going to match up with letter D. Okay, uh, and just so you guys know, in the future, whenever you guys see this symbol right here, delta, guys, you should know what that means, what delta means. Delta means change. And mathematically, what it means is you subtract an object's final momentum. I'm sorry, you subtract an object's initial momentum from its final momentum. So in other words, it's equal to final momentum minus initial momentum. Okay, so that matches up with A. Okay. Um, Again, guys, we're just going over some definitions. Look at number 4, vector. What exactly is a vector? Well, a vector is something that has both magnitude and direction. For example, at the beginning of school year, whenever we talked about velocity, velocity would be an example of a vector. And because remember when we said whenever you're talking about velocity, velocity depends on two things. It depends on how fast an object is going, and it depends on what direction it's traveling in. We call that a vector. So, just guys, just as velocity is a vector, momentum is also a vector quantity as well. That whenever you're talking about momentum, it's important that you talk about magnitude and direction. So, for instance, imagine an object is moving at 5 meters per second toward the east, and compare that to an object that's moving at 5 meters per second toward the west. Both these objects are said to have different momentums because they're moving in different directions. Okay, so so because momentum depends on direction, there's a word that we call that a vector. Any quantity that depends on direction and magnitude is a vector. Okay. So velocity is a quantity that depends on direction and magnitude. How big something is and where it's traveling. That is a vector. So, momentum is an example of a vector. Velocity is also an example of a vector. So 4 here matches up with C. A vector is something that has that has direction, and is something that refers to how big it is or how large it is. Okay. What do I mean when I say magnitude? Well, magnitude just refers to how much of something. So in other words, if you have an object that has a momentum of 25 kilograms meters per second, okay, the magnitude would be the number 25. Magnitude is just a measurement. It's a numerical measurement of how large or how small something is. So number 5 here will match up with E. Okay. Now, one more thing I want to introduce. Whenever you see this term here, P net, what does that mean? P net. That's just another way of saying net momentum. Okay. Guys, anytime you see net momentum, that's just a simple way of saying add up all the different momentums. So if you have multiple objects, and you add up all those momentums, you get what is known as a net momentum. So the sum of individual momentums is equivalent to net momentum. Okay. So now, with that said, guys, let us work out. Let us look at some numerical examples. All right, look at number 7 here. Number 7 says well, at the top here it says, which has more momentum, a bowling ball at rest or a bowling ball going 1 meter per second? Guys, as a general rule, in order for an object to have momentum, it must be zero. It must have motion. It can't have zero velocity. It must be in motion in order for an object to have momentum. And that should make sense to you guys because in momentum is the product of mass and velocity. If an object has zero velocity, it has no momentum. So therefore, if a bowling ball is at rest compared to a bowling ball in motion in 1 meter per second, clearly the bowling ball that's in motion is going to have the most momentum. Thus, the bowling ball at rest has zero momentum. Okay. What do you guys think right here has the most momentum? A very fast baseball or a very slow bowling ball? Well, it turns out, guys, that even though the bowling ball has more mass than a baseball, the key thing is here, it says the baseball is moving very fast. So since it's moving very fast, when we take the product of its mass and velocity, this object right here ends up having more momentum than this object because it's moving very, very fast. Okay. Now let's look at number 9. Which has more momentum? A 1,000 kilogram object at rest or a 1 kilogram object moving at 0.2 meters per second. Okay. So remember, if an object is at rest, it has no momentum. An object must be in motion in order to have momentum. An object at rest has no momentum. So a 1 kilogram object moving at 0.2 meters per second has the most momentum. Okay. Now let's get into the calculations that you're going to see in your assignment. First of all, before we work out number 16 through 18, I want you guys to notice something here at the top here. We have 4 different objects here, objects A, B, C, and D. And all of these objects, no, guys, I take that back. This is not 4 different objects. This is one object. This is one object that's moving, but it's at different positions. Okay, so in other words, notice the object is moving fast here, then it slows down, then it comes to a stop, then it changes direction. Okay, so excuse me, I said that wrong. This is not multiple objects. This is one object that has this is one object that's moving and is shown at different positions. Okay, so the question is, before I can answer any of these questions, the first thing that I want to do, I want to numerically calculate the momentum of this object at different positions. So, for instance, when the object is at position A, what is its momentum? Okay, so if the object is moving at 5 meters per second and it has a mass of 3 kilograms, remember what momentum is. Momentum is just mass times velocity. So with that said, what is 3 times 5? 3 times 5 is equal to 15 meters per second. Right? I'm sorry, those units are wrong. The units for momentum is 15 kilograms meters per second. Let me make sure I get that right. So that's the object's momentum at position A. What is momentum? What is its momentum at position B? Well, let's multiply. Let's find out here. So 3 times 2, that is 6 kilograms meters per second. Okay. What is its momentum at position C? 3 times 0. Well, since it's not moving, it has no momentum. So 0 kilograms meters per second. So this is momentum there. What is its momentum at position D? It's moving at 3 kilo. Well, it's moving with a mass of 3 kilograms, and it has a velocity of -4 meters per second. So 3 times -4 meters per second. Okay, that is equivalent to 12 kilograms meters per second, but it is a negative because it's moving to the left. Okay, so when the object is at position D, it has a momentum of negative 12 kilograms meters per second. So guys, that's how you calculate momentum. You just do mass times velocity. That's simple. Okay. 16 says, what is the object's momentum at position A? We've already figured that out. We see at the top it's equal to 15 kilograms meters per second. Okay. Now look at number 17. What does 17 says? Calculate the change in velocity between positions A and B. Guys, remember what delta means. Delta always means change, and it means take the final value and subtract it from the initial value, right? So if the object started off here, position A, and then a few seconds later it was here, position B, what we need to do, we need to subtract those two. We need to do B minus A. So the velocity at B okay, the object at the objects when it's at position B has a velocity of 2 meters per second. When it's at position A, it has a velocity of 5 meters per second. So the change in velocity, 2 minus 5, is just negative 3 meters per second. All right, let's keep going. And again, guys, we're not going to work out this entire page today. We're just going to do just enough problems, just so you guys can get started on the assignment that I'm going to post as soon as I get done with this. Look at 18. 18 says calculate the change in momentum between positions B and D. Calculate the change in momentum between positions B and D. Okay, so this is position D and this is position B. This was the final position, and this was the position at some time before that position. So, guys, as a general rule, whenever you calculate the change in something, so in this case we calculate the change in momentum, it's always equal to, the second value minus the first value. In other words, some final value minus some initial value. Okay. Since we're solely looking at position D and position B, position D would be the final momentum, which is negative 12, minus the initial momentum, which is 6. So the question is, what is negative 12 minus 6? That gives you negative 18 kilograms meters per second. So negative 18 would be the change in momentum between this position and this position. My computer's trying to freeze up on me. So you always do final point minus some initial point. Okay. All right, guys. Before I get done with this, I just want to do just these next two parts here, and then we're going to call it a day. Number 10 says, can an object have momentum in space? The answer to this question is yes, if it is in motion. Yes, if it has motion. If it has motion, it can have momentum in space. Look at number 11. Number 11 says, if you increase a moving object's mass, how does its momentum change? Well, that should be obvious. If you increase its mass, that means its momentum increases. So as one goes up, the other also goes up. Number 12 says, if an object changes momentum, there must be a change of what or what? Well, just look at the equation. If an object was to change its momentum, there must either be a change in its mass or its velocity. Okay. Everybody got that? Number 13 says, how can momentum be negative? Well, that's easy. If we have an object that's either moving to the left, if it's moving left or moving down, if it's moving left or moving down, it has negative momentum. Okay. If it's moving left or moving down, we say that it has negative momentum. Number 14 says, how can an object have the same speed and mass but change its momentum? So how can an object have the same speed and mass and change its momentum? Well, that's easy if the object turns around. So if it turns around and moves in the opposite direction. So if the object turns around, that would be one way it could change its momentum. So if it turns around and moves in another direction, clearly it changes its momentum, because momentum is an example of a vector, and that it includes magnitude and direction. Number 15 says, how can multiple objects have a net momentum of 0? Well, guys, that's pretty easy. If you have two objects that move at the exact same speed but move in different directions, they can have a combined momentum of 0. So, for example, imagine you have one object. So let's say we have a ball. Imagine that we have a ball moving at 5 meters per second in that direction. And we compare that to another ball. And again, we're assuming these balls have the same mass. And this ball is moving at 5 meters per second, but it's moving in the opposite direction. So if this ball here is moving in this direction, this ball here is moving in that direction, when you combine those momentums, what's -5 combined with +5? Well, that gives you 0. So to answer number 15, how can multiple objects have a net momentum of 0? You will put if they both move in the opposite directions. So if two objects, I'm trying to write this out. So if they move in opposite directions, and again, we're assuming that they have the same speed but move in opposite directions, it's possible that when you combine their momentums, you get 0. Okay. Okay, guys, let's do one more section here before I let you guys go. So we're just going to complete 19, 20, and 21, and I think we would have done enough examples for you guys to be ready to work on this assignment. Okay. So before I do number 19, 20, and 21, I want to calculate the momentum of these individual masses. So in this situation right here, we actually do have different masses. This is mass A, mass B, mass C, mass D, and we can clearly see that these masses are different. Okay, so let us calculate the momentum of each of these masses first before we answer these questions. Remember, guys, momentum is just a product of mass and velocity. So if you multiply mass and velocity, you get momentum. So if the mass here is 6 kilograms and the velocity is 5 meters per second, when you multiply those two, 6 times 5, what you get 30 here. So you get 30 kilograms meters per second for the momentum of mass A. Okay. What about the momentum of mass B? If this object here is 4 kilograms and has a velocity of 3 meters per second, then 4 times 3 gives you 12 kilograms meters per second. Okay, so that's the momentum of mass B. What about the momentum of mass C? This object is not in motion. Anytime an object has zero velocity, it has zero momentum. Okay, so 0 kilograms meters per second. That's our momentum for mass C. And lastly, mass D. What is our momentum? So now this object here is moving is moving toward the left, so that means its momentum must be negative. So 6 times 2 gives me, in this case, I get negative 12 kilograms meters per second. So here we actually have a negative momentum for mass D. Okay. Now, with that said, guys, look at number 19. 19 says, calculate the net momentum of objects A and B above. Okay. Guys, remember what I said net momentum means. Net momentum means you just add up the individual momentums. So if this momentum here is 30, and this momentum here is 12, when I add up those two numbers, 30 plus 12, my net momentum is 42 kilograms meters per second. So that is my net momentum for number 19. Okay. What about the net momentums of B and D? Well, guys, look at the momentum of B, and look at the momentum of D. Remember, net momentum means add up those momentums. So when I combine those momentums, so basically positive 12 combined with negative 12. When I combine these two numbers here, what I get is 0. So the net momentum for objects B and D is just 0 kilograms meters per second. And lastly, look at number 21. Number 21 says calculate the net momentum for all 4 objects. Okay. Net momentum for all 4 objects means I'm going to take 30 plus 12 plus 0 plus negative 12. Guys, when you add up all those numbers, because that's what net momentum means, it's the sum of all the individual momentums. When you add up all those numbers, okay, so the positive 12 and the negative 12 cancel each other out, and so what you're left with is 30 kilograms meters per second. Okay, guys, I have just done enough examples. I have just done enough mathematical examples for you guys on momentum, so that you guys can kind of work this stuff out yourself. Okay. So let me go ahead and stop sharing my screen. Now, oh, and by the way, for anybody who's just now coming on, let me put the attendance form in the chat box for you. Now, before I leave, I just want to say one more thing here. Is that I told you guys at the beginning of this class that defining momentum in this way is very useful when it comes to analyzing collisions. It's important that we assign numerical values to the motion of certain objects for that purpose. And here's why it's important. One of the things that help demonstrate this is what is known as the Newton's cradle. Okay. I'm pretty sure some of you guys have seen this before, a Newton's cradle. Guys, it turns out that anytime you have collisions in nature, anytime you have collisions, the total momentum in that collision stays conserved, means it stays the same. So, for example, here's what I mean by this. So, look at this ball here. If I take this ball here, and I force this ball to collide with this ball, there's a transfer of momentum from this ball to this ball to this ball to this ball to this ball. And the point is that momentum, the total momentum, in this collision stays conserved. So notice, guys, if one ball goes in, one ball comes out. Okay. Same thing here. So what if I increase the momentum of my system by getting 2 balls, right? Because if I increase the mass, I'm now increasing momentum. Well, so notice how momentum stays conserved. Notice how if 2 balls go in into the collision on this side, 2 balls come out on that side, right? So the basic idea here is that the momentum is staying conserved. Okay. If I do 3 balls, if 3 balls go into the collision, then 3 balls come out on the opposite side. So the point is I'm getting at, there's a certain measurement of motion that stays constant in the collision, right? There's a numerical value to motion that stays constant. If I take 4 balls, if 4 balls go into the collision, 4 balls come out. Okay. So that just kind of gives you guys an idea of why is it that physicists quantify motion in such a way. It's because it turns out that has very real world applications whenever you're analyzing car crashes and collisions and things like that. Like insurance companies actually depend a lot on numerical measurements and momentum. So just something I wanted to express to you guys, and hopefully that makes sense. Okay. Any questions before I let you guys go? All right, guys. I'm gonna try to post this video on YouTube and send you guys the link. If I can't post it on YouTube, I'm gonna post it on my Google Drive. But hopefully, I can post it on YouTube. Anyway, if you guys don't have any questions, you guys are free to go. Remember, the assignment will be posted soon. Give me about 5 minutes, and I'll have the assignment posted for you in Schoology. Have a good day, everyone.